So we're going to start talking about 3D parametric curves, curves in three-dimensional space that depend on some time variable. But I thought it would be a good idea to start by reviewing some basics of 2D parametric curves. So let's just look at some basic examples that maybe you're already very much familiar with. So in general, when you talk about parametric curves, the idea is that you have x and y not as functions of each other necessarily, but as functions of some third variable, t. Intuitively, we like to think of t as time. So how do you actually figure out what picture that looks like in the xy plane? Well, you try and eliminate the t variable. Here, one way you could do it is to say, well, if x is cos t, then that means t is the inverse cosine of x. But if t is the inverse cosine of x, then you plug that in to y being equal to sine t, then y is equal to sine of inverse cosine of x. Okay? And it turns out that that's actually going to give you something like the square root of 1 minus x squared. Where does this equality come from? It looks very bizarre. Well, you might remember from lower level calculus classes, you would always draw this triangle, this right triangle. You'd call one of the angles, in this case, I guess we're calling the angle t. And then if x is cos t, then, well, cos is adjacent over hypotenuse. So x divided by 1 would be cos t. So it works out. I mean, x divided by 1 is just x. But then that would force this side by the Pythagorean theorem to equal the square root of 1 squared, which is just 1 because that's the hypotenuse, minus the other side squared, which is x squared. So that when you take sine of t, well, because t is cos inverse of x, sine of t would just be opposite over hypotenuse, and that's where that comes from. So it's a little bit bizarre. A nicer way of thinking about it in this particular case is to just look at what happens if you square x, square y, and add them together. I mean, if you take x squared, that's the same as cos squared t, because x is cos t. Similarly, y squared is just sine squared t, and by now you should know this trig identity by heart. Cos squared plus sine squared of anything, as long as they're the same angle, is always going to give you 1. So x squared plus y squared equals 1 is another way of obtaining the equation, which of course is the same as saying y is equal to radical square root 1 minus x squared. So if we actually graph this, well, what does it look like? Well, by now you guys should probably already know x squared plus y squared equals 1 describes the unit circle centered at the origin. There it is. So there's not a whole lot of surprise there. Okay? But what does this whole t business really do for us? Well, here's a rough picture of what this all looks like. You have a circle, and the idea is you want to think of this circle not just as laying flat in the xy plane, but as actually being drawn out by following the course of a certain point, like that red dot. So when t equals 0, think about that. When t equals 0, cos is 0, so if I recall, x is cos of t and y is sine of t. So cos of 0 is 1, sine of 0 is 0, so the x and y coordinates are 1, 0, which is precisely this point here that I've drawn here in red. That represents the point when t equals 0. All right, so maybe I'll write it this way. T equals 0 implies x comma y, the point we're interested in is cos 0, comma sine 0, which is just, of course, 1, 0, which is that red point there. On the other hand, when t is equal to pi halves, we're using radians here, cosine of pi halves is 0, sine of pi halves is 1, that represents this point up here at the top. Similarly, t equals pi radians would be this point over here, right there. So really, if you imagine what's happening, if you start at time t equals 0 and you just draw that red point there, then what's happening is as t marches forward, this red dot is tracing out the circle. It's leaving behind this residue, this blue residue. Imagine there's no circle there, and we're just kind of tracing that circle for the first time. Pi halves seconds in, we're right there at the top. We keep going, pi seconds in, we're right here. And by the time we get back to 2 pi seconds, we're right back where we started. And we just continue. And if you rewind time, you're going back in the opposite direction. So really, with these parametric equations, what you want to think of them as is t represents time, and x of t, x is a function of t, and y of t, represent the xy coordinate at time t of whatever this red particle is. So whatever shape it traces, so here's an animation using Microsoft Mathematics, there's our circle. Let's click the trace button, and you can see that we're just marching along the circle. And we hit the top of the circle when t is equal to 90 degrees, and here t is equal to 180 degrees, etc., etc., and you just keep going around the circle just like that. Okay, so let's hop back here and let's consider some other examples. What about x equal to 2 cos t and 5 sine t for y? Well, now one thing you'll notice, it's a little bit awkward here, but you'll notice that cos t is the same as x over 2, or 1/2 x. Similarly, sine t is 1/5 y, or y over 5. So if you square this and square that, you're just taking cos squared plus sine squared. In other words, cos squared plus sine squared is equal to, in this case, 1/2 x squared plus 1/5 sine, or y squared, sorry. I have it here in green, and that's going to equal 1. Okay, so to see what this graph looks like, described by this equation. So again, we're trying to eliminate the t variable. We could say x over 2 is inverse cosine, then plug that into sine, and then use our little triangle as we did in previous calculus classes. But let's make life a little bit easier and just jump to it. If you distribute the square, you get 1/4 x squared and 1/25 y squared. And let's see what that graph actually looks like. Okay, let's zoom out a little. Bizarre. Oh, by now I should have seen it. This is very strange. Okay, well, in any case, we can do it here on this Microsoft Mathematics. So we'll jump back to the parametric equations, and now x is not just cosine, it's actually 2 times cosine. And y was 5 times sine. Okay, and if we graph these, well, we don't get a circle anymore, we get an ellipse. And again, as you trace it, you're kind of just going around the ellipse, back and forth. So multiplying or scaling the x and the y has the effect of kind of squashing the circle in one direction or another to give you an ellipse. So there's just another example of a parametric formula. So usually you want to solve for t as a function of x, plug it in for y if you don't know what to do. If we actually did that, I guess t would equal the inverse cosine of x over 2. So then y would equal 5 times the sine of the inverse cosine of x over 2. And you'd play your little right triangle game and you'd come up with another formula, or you could just do it in this way. That's a nice trick for an ellipse. Not sure why it didn't work here for the basic math plugin in OneNote. But let's look at an even simpler example. What happens, just because this is going to be useful later on, when x is equal to t, when one of the variables is just straight up equal to t, and the other variable is a function of t? Well, solving this for t is a piece of cake. If t is the same as x, then just plugging in x here where we see t, y is equal to sine x. And I'm sure you guys already know how to find the graph of that. It's just a sinusoid, but let's just make sure that the program is working correctly, and there it is. There's the graph, y equals sine of x. So you'd want to imagine here, let me even insert that. There we go. So again, what you'd want to imagine is that as time marches forward, there's my dot, it's just going to trace out this path as time marches forward, or rewinding time, time going backward would look like that. So it's just a function of t. Your x coordinate matches up with your t perfectly, and your y is just sine of whatever your t coordinate is. So you're just tracing out that kind of path right there. Of course, here one of the things that's nice is that you don't always have to solve for y in terms of x. So another example, a very similar example, is what happens if y is t and x is sine of t. Well then, you just plug in y there, and you'd think of x as a function of y. X would be sine of y. And if you graph that, it's going to look like a sinusoid, but flipped in a different angle, so it's going vertically instead of horizontally, because now x is a function of y. Let me just insert that, and then just draw it again. And so now we're kind of going upwards. As time marches forward, our x shuffles back according to the sine function, and y is just always t, or rewinding time, time going backwards, looks something like that. So it's a simple enough picture. You want to imagine your curve as being drawn by a point moving along it with respect to time. But it's important to understand this 2D picture before we understand the more complicated 3D.